Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 62 and this time around we will be modeling the RF part of the 22 nanometer CMOS FDSOI cryogenic device. So, basic definitions which you already know, but let me go through it once again. F suffix T is basically referred to as the cutoff frequency and is basically defined as the short circuit current gain. So, that is that frequency or that frequency when your short circuit current gain becomes unity. Unity in terms of log scale will be 0 dB, right, because it is 20 log output by input. So, when my output by input is equals to 1, log 1 equals to 0 and therefore, I get a 0 dB gain. We define that frequency as the cutoff frequency, which means that if you go anywhere above that frequency, your gain will be further less than that, you will get a negative dB gain. Your means output will be smaller as compared to input. And how is it done? It is basically the short circuit current gain is defined as H21 and it is extracted by extrapolating H21 with a slope of minus 20 dB per decade over a 1 to 20 gigahertz limit range. So, what you do is basically you plot the graph of H21 and then you try to, when it goes down, you check where you have the around the 20 dB slope, you just extrapolate it backwards and you check where you get unity gain in terms of current and that gives you the value of the frequency. So, if the unity gain comes somewhere here, then this is my Ft which you see, this is 0 dB which I will get, right. So, let me change the color of this. What is Fmax? Fmax is basically the maximum oscillation frequency and is defined as the frequency at which the Mason's unilateral power gain, forget about Mason and all these things, is power gain basically becomes unity. So, output power by input power is unity and it is again extracted using 20 dB per decade extrapolation of the power gain, right. Now, why we are referring to 20 dB per decade? Because we are assuming that it is a first order sort of a network and my attenuation is typically at the range of 20 dB per decade which we get. Now, both Ft and Fmax are basically derived from de-embedding the S parameter to remove the parasitic effects. So, what we do is we have an active device, right, and we have parasitics attached to it. So, we need to de-embed initially in order to extract the value of Ft and Fmax, right, and they are done to remove the parasitic effects to a larger extent. So, in this paper which I had referred to you earlier, which was on characterization and modeling of 22 nanometer FDSOI, it was done, the cryogenic characterization was done on a Keithley equipment, right, which is 4200 SCS parameter analyzer and the RF measurement setup consisting of ground signal ground probes. They were the ground signal ground probes and the pitch of these probes, distance between the two probes is approximately 50 micrometer and they have used what is known as an 8722D VNA vector network analyzer, right, for extracting the value of the S parameter. Now, the S parameter were actually measured right from 300 Kelvin to 5.5 Kelvin. And they were done on 18 nanometer and 28 nanometer LG FETs, right, LG FET here. How many? With 16 gate fingers, they were used 16 gate fingers and 0.5 micrometer is the width of the fingers and the frequency range was 0.5 to 35 gigahertz frequency range, the extraction was done. And they were done both at saturation as well as in the pre-saturation region. Saturation was keeping VDS equals to 0 in cutoff under cold FET condition. So, let me define again here an important parameter here. If you look at the point, there are two types of applications. We do a cold FET and hot FET manipulation or evaluation. In cold FET, we use VDS equals to 0 volts, VGS is equals to 0 and 0.2 volts and we use a and when we go for saturated conditions, this is cold FET and because VDS equals to 0 you do not have a lateral or a longitudinal electric field available to you, whereas in saturation you can use VDS to be equals to 1 volt and mod of VGS which you use is 1.2 volts, 1.2 volts in saturation. The S parameter of the on chip open and short circuit currents are measured in this paper for all the temperature ranges, and they have done a two step de-embedding technique in this case for extracting the value. And what they have found out is that the series combination of interconnects will give you Y short minus Y open. So, the Y of the transistor they are finding out, the Y parameter of the transistor is effectively equals to Z device under test minus Z series to the power minus 1, right, minus Y open circuit. So, Y of the transistor is Z DUT is the Z parameter of the measured device. This is the measured Z parameter of this device, Z11, Z12, Z21 and Z22, the 4 parameters which are using, and these are actually used to calculate the value of FT and Fmax at a later time. Okay. So, this gives you a brief idea about the cryogenic RF characterization which you get for a 22 nanometer FDSOI, and the figure of merit will have intrinsic frequency performance gain of MOSFET at different cryogenics temperature. Now, let us find out H21 versus frequency. H21 is basically my short circuit current gain, NMOS and PMOS circuitry. So, on the right hand side if you see, this is for various temperature, this is for 300 Kelvin, this is for 70 and this is for 5.5. The gate length is kept to be the same and the value of VDS is kept to be 1 volt. So, that is also kept same to a larger extent, and what we are doing is we are varying the value of H21 with respect to frequency. Right, we are varying the value of H21 with respect to frequency and we are extrapolating with a minus 20 dB per decade attenuation in the value of H21. Now if you look interestingly, they all look almost the same quantitatively. However, at 300 Kelvin if you look, both NMOS is basically the red one, these are all NMOS, red one is basically my NMOS and my blue ones are basically the PMOSs, and they have been under the role of 20 dB per decade. Now, the reason you are seeing it 20 dB per decade is why the graphs are linear is because of the log scale which we are referring to, right. And the unity gain for NMOS, the unity gain frequency is found out to be 367 gigahertz for NMOS and understandably so less for PMOS, because PMOS carry this lesser amount of current and therefore, the unity gain will be also smaller, FT will be relatively smaller. At 77 K, how do you find out is you just that is what you are doing, right. You did a lot of measurement for low frequency and then you start extrapolating it backwards at 20 dB per decade, where it cuts the x axis, that happens to be your sort of the value of your FT. Now, you can see in most of the cases that at 700 Kelvin there is a reduced scattering, improves the mobility, and therefore, FT is pushed higher than at the room temperature. So, it is slightly higher than the room temperature, whereas at 5.5 Kelvin it is still larger, where you use an improvement is very large. For NMOS the improvement is FT is around 494 gigahertz and for PMOS it is about 337 gigahertz. So, if you compare 300 Kelvin right up to this one, then you can see this is 367 here and this is 494 here, right. So, typically if you see approximately the difference between the two, it is about 130 gigahertz which you see, right. So, 130 if you divide by 367, this comes out to be approximately one third of approximately 33% improvement will be there in case of Kelvin, which means that if you do not do any changes in the device characteristics, I would expect to see a larger variation in the value of H21 when I do in case of 5.5 Kelvin I get a much better improvement in the value of H21, and this is primarily to do with enhanced currents, and that is also because of reduced scatterings. Primarily the phonon scattering is reduced, thermal scatterings are reduced, mobility goes high and you are able to sustain a much larger value of the FT. Now, let us look at FT with respect to the ratio of drain current to per unit width. So, on the x axis we have a normalized drain current. Normalized, when I say normalized, so this is basically my normalized drain current, right. This is referred to as a normalized drain current. Normalized, why? Because with respect to width I am normalizing it, right, and that is the reason we define this to be as a normalized drain current. And if you plot the FT value with respect to the normalized drain current with respect to normalized drain current. So, when I say and this is for the gate length of 80 nanometer, and the first graph is for VDS equals to 1 volt, and this is for NMOS, and for PMOS it is VDS equals to minus 1 volt. Understandably, for everything else remaining the same, first of all you see your FT is lower as compared to PMOS as compared to NMOS. For the all other parameter remaining the same, PMOS gives you a relatively a lower value of FT as compared to that of NMOS. But in both the cases, be it NMOS or PMOS, as the temperature goes on reducing, the FT max value goes on increasing, right. The FT increases with the current gain density, becomes maximum and then starts to reduce. The increase is primarily because degradation in the current is higher, and therefore, you get a much larger value of F max, but beyond the point when the current increases, series resistance comes into picture, mobility degradation comes into picture, and therefore, your FT starts to fall down beyond a particular limit. Beyond a particular limit, when I say it is approximately 0.4 is the limit where I can see I can get a reduction in the value of FT, right. So, FT actually starts to go down after approximately 0.4 in case of NMOS, and typically somewhere around 0.4, 0.3 to 0.4 in case of. Two things to be noted here again, that in NMOS the drop in the value of FT max is much larger as compared to Pmax. Pmos tends to saturate beyond a particular point, right, it does not show a big decrease, whereas in NMOS I see a big decrease in the value of the FT max. And again the reason comes out from the fact that electron degradation is much higher as compared to hole degradation in terms of mobility and the series resistance. So, that is the reason you see this getting dropped. Two things to be noted here is why therefore, with temperature increasing temperature FT max drops, you can understand that point very easily and you can actually extract it. But for very high values of ID, normalized current, you see for a very high value and relatively a low value, these two edges, if you see for both NMOS and PMOS, they are almost touching each other. That means that there is no much difference in the value of FT. However, as you make the ID value go on increasing, the distinguishing factor of FT comes into picture, and that is the reason you see an FT first of all increasing and then becoming again. So, the difference is going on decreasing once again in this case. So, the FT versus ID versus W graph gives you a value which is there. Peak FT is improves from 268 gigahertz at 300 Kelvin to 337 at 5.2 Kelvin, whereas in case of NMOS FT is 3.6 gigahertz at 300 Kelvin and 494 in case of 5 Kelvin, which we have already seen in our previous discussion. Now, if you plot FT with respect to temperature for NMOS and PMOS, then this shows a monotonically increased or improvement in the value of FT as the temperature goes on decreasing. Almost linear betterment in the value of FT with temperature, and I have kept it almost in the saturation region. So, your overdrives are large, you are using a large amount of drain current. So, the currents are also not reducing in any way, and therefore, your NMOS and PMOS are also giving you a higher value as the temperature goes on decreasing. Again, as you can see here, NMOS has got a much larger value as compared to PMOS. Point to be noted therefore, that cryogenic improves the frequency dependent terms which is available to us in case of a device. Now, and this is a point of which you can all discuss within yourself, that around 150 Kelvin, if you see, you can see two specific slopes in the value of FT around 150. So, the one is the one around 150 Kelvin, till this much it is almost linear for both NMOS and PMOS, and it is also partly linear beyond 150, but the slope changes in this case, right. Slightly it changes, it becomes slightly flatter in case of a reduced value. Just think about it, why is it like that? You will get the answer in this paper as well, but you can I am leaving this exercise to you to in this case. I am also leaving an exercise, what will happen if I reduce my VDS from 1 volt to 0.1 volt, right. Then how can I get the value of, or if my VDS reduces drastically to to a very low value, how do I get the value of Ft in this case, right. This needs to be found out in this case in this right hand side figure which I am showing here. But the key point or the takeaway point from all these discussion is that the cryogenic operation significantly boosts the value of your Ft to a larger extent. Okay. Let us look at the unilateral power gain, right, also referred to as MUG. This is also referred to as Mason's unilateral power gain, referred to as MUG versus frequency. So, this is I am plotting your MUG in dB versus frequency. The same concept again here, look at the 20 dB slope where it cuts the x axis, that is your unilateral power gain. Unilateral power gain primarily means where P out by P in is equals to 1. So, basically unilateral power gain basically means P out output power by input power is approximately equals to 1, which I see. At 300 Kelvin, if you look at its approximately for NMOS is 373 gigahertz and for PMOS it is 288 gigahertz, which you see, right. NMOS has got a relatively a slightly higher value of MUG as compared to a PMOS. At 300 Kelvin the value becomes slightly better, and at 5 Kelvin it much becomes at 497 and 372 for PMOS in a sense, right. So, it is almost increasing to a larger extent as you make your temperature go down to 5.5 Kelvin or so. We are using a gate length of 18 nanometers and drain to source voltage of 1 nanometer. One important point to be seen here is, unlike the previous graph which was this one, where you see that even at very low frequencies your H21, which is short circuit current gain, is still going on increasing for a low value of frequency. Here interestingly it tends to saturate at a very low frequency. The what saturates the unilateral power gain frequency basically U gates rolls off. It basically rolls off at minus 20 dB, but shows a saturating tendency at for all temperature 5.2, 300 Kelvin and even at 77 or Kelvin. It shows a basically tapering off, which means that the value does not go on increasing as you reduce the value of your frequency. This is more to do with some excessive values of other parameters which tries to degrade the value of your unilateral gain power, which is U in this case. Okay. This gives you a brief idea about the value of these currents. Now, let me come to, we have again repeating the same slide here, and I wanted to show you here that the this is for Fmax improvement is about, so I had Ft I have done, this is Fmax, looks almost the same. So, Fmax is again repetitive as compared to Fmax, and the first two sections of the slide, the first two, one which is this one and this one, typically as you can see Fmax is also reduced for PMOS as compared to NMOS, everything else remaining the same, and shows you exactly the same behavior as an Ft in this case. And the value Fmax increases with current density, and then first it peaks around 0.2 to 0.4 and then it starts to drop down. Similarly, at very low values of IDS by W, the normalized current gain, and at very high values, the difference between the various temperature ranges are almost equal, they are almost the same. Whereas, when you talk about PMOS, the difference is almost the same at low temperature, very small, there is a difference, but not, there is also a small difference at high, but it increases at somewhere around 0.2 to 0.4 milliampere per micrometer, right, normalized current. And the peak Fmax, if you plot peak Fmax versus frequency, the last graph here, then you see approximately 30% increase in the value of your NMOS peak power, peak Fmax as compared to your PMOS. So, PMOS is relatively lower, right. And the interesting case here is the difference goes on increasing as you reduce the temperature. For case of Fmax, the difference between the Fmax of NMOS and PMOS goes on increasing as you increase the value of your PMOS and NMOS. Okay. So, and this is for VDS again 1 volt and LG is equals to 180 nanometer. So, the experiment has been done on 80 nanometer, but you can extend this work on a simulation at 22 and 28 nanometer for all practical purposes. So, this was a sort of a good idea to look into this range, and let me recapitulate the results of cryogenic RF characterization. What we have seen is both Ft and Fmax shows a drastic improvement at cryogenic temperatures because of a much enhanced carrier mobility, and this is primarily because of reduced phonon scattering. Since my mu phonon has actually reduced, scattering has reduced, my mobility actually starts to increase. The overall mobility starts to increase because my scattering reduces, especially the phonon scattering starts to reduce, which is why phonon, because phonon is basically temperature generated particles, and therefore, since the temperature has actually dropped down to millikelvin or around Kelvin, we see a much reduced phonon scattering in this case. We have seen that my max is 494 gigahertz for NMOS and 337 for PMOS at 5.5. So, this is 5.5 data, and my F max is 497 and 5.5 for this thing, and therefore, I see to 25 to 35% increase or change in the value of FTF max at 5.5 as compared to 300 Kelvin. The drain current peaking, ID by W peaking, is almost independent of temperature. It peaks at around 0.4 ID by W, which we have seen, and these are all consistent with 22 nanometer FDSOI technology also, and as per the previous methodology which we have done or other papers which have reported at 22 nanometer, and the values are recently close to the value of FDSOI. With this, I think I will close here, because the next part we will discuss more about parasitic capacitances, which we will take up in the next turn. So, let me recapitulate what we did in this half an hour of lecture. We looked into primarily on what is the meaning of FT, F max and unity gain, power gain, and then we tried to see how these values will be a direct function of the temperature, and the overall conclusion was that at cryogenic temperatures all the parameters shows an improvement, and this is primarily because of reduced phonon scattering and increased mobility of the charge carriers. We also looked into the fact that if I vary the value of ID by W, how does my vary, and you can see that it basically the difference changes with temperature for NMOS and PMOS. The second important part was PMOS showed a lower value of all these parameters as compared to NMOS, again a point which is well taken and understood physically also. The last point is that we need to do double embedding in this case in order to remove the parasitic capacitances. So, this takes care of our understanding of cryogenic RF characterization. In the next turn, we will see the capacitance loading or the parasitic capacitances for the devices. Thank you very much for your patient hearing.